Hello everyone, today we are going to cover a chapter out of the Principles of Radiographic Imaging in Art and Science by Adler and Carlton. And in this presentation we're going to be talking about radiation concepts and the structure of matter. So radiography is the recording of images that are created by the use of X-ray energy. And as pointed out very nicely by Adler and Carlton, radiography is both an art and a science. There's the physical science part of how X-rays are created, how they penetrate through the body or are absorbed, but it's also an art. We, the radiographers, are artists, basically, in how we position our patients to get the most ideal radiographs. There's definitions that are talked about. We talk about science, the use of knowledge in an organized and classified manner. We talk about natural science, the study of the universe and its contents, and that can be divided into two categories. We can talk about physical science, or we can talk about biological science. Our emphasis is on physics. It's a branch of physical science that studies matter and their interrelationships. There's a lot of definitions that go along with the beginning physics. First of all, we've talked about this before, matter, the substance that comprises all physical objects. It has shape, it has form, and it occupies space. Mass is the quantity of matter contained in any physical object. And remember, the unit of mass is the kilogram. Weight is the force of an object exerted under the influence of gravity. Remember, you can't have weight unless you have gravity. The unit of weight is the Newton. Remember, I had mentioned that a good way to remember that is that you can't have weight without gravity, and the scientists, they came up with the whole concept of what we know as gravity is Newton. So the unit of weight is the Newton. The book also talks about substances and mixtures. A substance is a material that has definite and constant composition. And then if you have substances and you put them together, now we have a mixture. So a mixture is the combination of two or more substances. And substances can be either simple or they can be complex. If they're simple substances, we call them elements. And if they're complex substances, we call them compounds. So an element is a substance that cannot be broken down into any simpler substance by ordinary means. And there are 92 naturally occurring elements. When two or more elements are chemically united in definite proportion, well, then we have something called compounds. So compounds are formed when two or more elements are chemically united in a definite proportion. An atom is the smallest particle of an element. So if I had a block of gold, for example, and I kept breaking it down and breaking it down and breaking it down and breaking it down and breaking it down, eventually I would get to one atom of gold. At that point in time, I couldn't break it down anymore, otherwise it would no longer be gold. A molecule is formed when two or more atoms are chemically united. A molecule is the smallest component of a compound. So if I have a compound, in this case, here is a diagram showing you a sodium, which is joined with chlorine to give you sodium chloride, and this is a molecule. Okay, when sodium, one atom of sodium joins with one atom of chlorine, we have a molecule of salt. We can't break that down any further because otherwise we would just have sodium or we would just have chlorine and it would no longer be salt. The degree of attraction between atoms and molecules determines if the substance is a solid, a liquid, or a gas. For example, if there's weak attraction between the atoms or molecules, we call this a gas. If they start sticking to get together a little bit better, well, then we call that a liquid. And if there's a real strong attraction between either the atoms or the molecules, we call that a solid. And some substances can exist in all of these states. If you think about water, for example, we can have water in its natural form, which is a liquid. We apply thermal energy or heat to it, and now it turns into a gas. We loosen up the bonds. Or if we take away thermal energy, we make it colder. Now the bonds become more solid, and we have ice. Energy is the ability to do work. Energy emitted and transferred through matter is called radiation. Albert Einstein in 1905 described the unique relationship between matter and energy. And according to Einstein, matter and energy are interchangeable. The basis of Einstein's work is the law of conservation of energy, which says basically that matter and energy cannot be created or destroyed, but it can be converted from one form to another. We said that the smallest particle is the atom. Well, the atom actually can be divided into three basic subatomic particles. Remember, sub means below, so subatomic particles. We have protons, which are positively charged, and the positively charged protons are located in an area of the atom which we call the nucleus. Neutrons have no charge. They're in the nucleus as well, but they don't have any electrical charge. And then to even out the electricity between the atoms, so to speak, we've got those positive protons. We've got negative electrons then that circle around at very distinct distances around the nucleus, which we call either orbits or shells. In 1913, Niels Bohr, a Danish physicist, proposed a model of the atom which is likened to the solar system. And in his model, he said that the center of the atom was like the sun. And then we have the planets which orbit around the sun, just like the electrons orbit around the nucleus. And although this is a rather simplistic model of the atom, we still use it today, especially in our field of radiography when we study physics. If you have protons and neutrons together, we call these nucleons, and they're located in the atom's nucleus. Electrons are located outside of the nucleus, and they've got a relatively insignificant mass compared to the nucleon. So the bulk of the weight of the atom is in the nucleus. Electrons cannot be divided into smaller parts, but protons and neutrons can be divided into subnuclear structures, and we call these quarks. And there are the quarks, the names of them. Interesting names. We've got up, down, strange, bottom, top, and charm. So those are the quarks. So the number of protons in the nucleus is known as the atomic number, or Z number. So how many protons in the nucleus is the atomic number, or Z number? Why is this important? The atomic number gives an atom its identity. It tells you what type of element it's an atom of. For example, if I were able to take a nucleus and count out how many protons are in the nucleus and I came up with 56, I would know then this is an atom of barium. So if an atom gains or loses a proton, well, then it would become an atom of a different element altogether. So the number of protons tells you what type of an atom of what element it is. The number of both protons and neutrons in the nucleus determine an atom's mass number, or its A number. So protons and neutrons together are called the A number. The mass of the particles of an atom is sometimes described as its atomic mass units. In science, this is more exact than simply stating the mass number. An atom that loses or gains a neutron, that's now called an isotope. And an atom that gains or loses an electron is called an ion. So when we look to the side here, we can see up at the top, if I had an atom and it had 2 protons in its nucleus, I would know that that is an atom of helium. There is the chemical symbol for helium. And then you have its atomic mass, which is very specific there. You see 4.003. Down at the bottom, this is the typical way that we write out when we're talking about an element, the mass number and the Z number. So your mass number, your A number, goes on top. It's the superscript. And then the subscript then would be the atomic number. So in looking at this, this is an atom of carbon. It tells me that carbon has 6 protons in its nucleus. And then it tells me the mass number is 12. Well, what is the mass number? It's the number of protons and neutrons. So if I took 12 minus 6, the 6 protons, what am I left with? 6. 6 what? 6 neutrons. The distance from the nucleus determines the energy level or the shell the electron occupies. Each shell has a certain amount of binding energy, and this is measured in electron volts, which holds it in its orbit around the nucleus. The closer an electron is to the nucleus, the greater is the binding energy. Very, very important fact, especially in radiography when we're going to talk about interactions of X-ray and matter, or we're going to talk about other things as far as radiography is concerned and the physics behind it. So the closer an electron is to the nucleus, the greater is its binding energy. The shell closest to the atom's nucleus, it's called the K shell. The next shell out is the L shell, and then the M shell. So if we look at the diagram off to the side there, we can see K, L, M, N. And in these shells, there is actually a maximum number of electrons that can be in there, which we'll talk about in just a moment. But just to point out that a K shell electron is going to have greater binding energy than an L shell electron. An L shell electron is going to have greater binding energy than an M shell electron, and so on. The shell number is referred to as the principal quantum number. So the first shell out from the nucleus, the K shell, is a principal quantum 1. The second shell out, L shell, principal quantum number 2, etc. In a neutral atom, the number of electrons equals the number of protons. In a neutral atom, the number of electrons, the number of negative charges, equals the number of protons, the number of positive charges. So if I've got an atom that has 10 protons, then that atom has 10 electrons. I mentioned that there's a maximum number of electrons that can be in a given shell, and there's a little formula that you can use to calculate that. The maximum number of electrons that can occupy a given shell is defined by this formula, 2n squared, 2n squared, okay, where n is the principal quantum number. So if I wanted to figure out what is the maximum number of electrons that can be in the K shell, well, the K shell, the first shell out, has a principal quantum number of 1. 1 squared, 1 times 1 is 1, times 2 is 2. The maximum number of electrons that can be in the K shell, then, is 2. Let's do the L shell. Well, the L shell is the second shell out, principal quantum number 2. 2 squared is 4. 2 times 2 is 4. Times 2 is 8. So the maximum number of electrons that can be in the L shell is 8, and so on. There is a rule called the octet rule. The octet rule is the number of electrons in the outermost shell never exceeds 8 electrons. So in the outermost shell, you will never have more than 8 electrons. Atoms are most stable if they have a filled outer shell. Atoms may gain or lose, these are called ionic compounds, or share, which is called covalent compounds, electrons to achieve this stability. And there is a certain group of elements which are known as the noble gases, like helium, neon, argon, krypton, xenon, and so forth. The noble gases are found in group 18 of the periodic table, which we're going to talk about in a moment. All noble gases have the maximum number of electrons possible in their outer shell. Okay. 2 for helium, because helium only has 2 protons, so the maximum number of electrons it have is 2. But it's 8 for all of the others, and this makes them very stable. The noble gases are described as being inert. And basically what that says is that, chemically speaking, these gases will not want to come into any chemical combination with another gas because they already have 8 electrons in their outermost shell. Here is a diagram of the periodic table of the elements. The periodic law of chemistry recognizes that properties of the chemical elements are periodic functions of their atomic number. That is, the number of protons within the element's atomic nucleus. The periodic table is an arrangement of the chemical elements ordered by atomic number in columns, which are called groups. And this is going to be important to note. The columns are called groups, and the rows going across are called periods. So the periodic table is an arrangement of the chemical elements ordered by atomic number in columns, groups, and rows, periods, presented so as to emphasize what are called their periodic properties. Now, who came up with this? A Russian scientist during the mid-1800s named Dmitry Mendeleev developed the first periodic table of the elements. So while attempting to organize the elements according to their chemical properties and atomic weight, Dmitry Mendeleev developed the periodic table and formulated the periodic law. His classification revealed recurring patterns, which he termed periods. Because of this, he left spaces in his table for elements that he correctly predicted would be discovered, because not all of the elements were discovered. His forward-thinking attitude extended into his politics as well as his classroom, and Mendeleev was a popular but a very controversial professor. A little bit about the periodic table of elements. The elements are arranged in increasing order of atomic number as you go from left to right across the table. The horizontal rows are called periods, and the vertical rows or columns, I guess would be better, are the groups. A noble gas is found at the right side of each period. And there's a progression from metals to nonmetals across each period. Elements found in groups, like the alkali group, the halogen group, they've got similar electronic configurations. The number of electrons in the outer shell is the same as the number of the group. The block of elements between groups 2 and 3 are called transition metals. These are similar in many ways. They produce colored compounds. They've got variable valency, and they're often called catalysts. They're elements that speed up chemical reactions. Elements 57 to 71 are known as the lanthanide or the rare earth elements. This was really important with radiography as far as screens were concerned when we were using screens for screen film radiography, because those were the elements that gave off light when they were struck by X-rays. Those were the elements that were in the screens, like gadolinium, for example. These elements are found on Earth in only very small amounts. Elements 90 to 103 are known as the actinide elements. They include most of the well-known elements which are found in nuclear reactions. The elements with larger atomic numbers than 92 do not occur naturally. They have all been produced artificially by bombarding other elements with particles. The number of electrons in the outermost shell determines the chemical or combining characteristics, or what we call the valence of the element. So the valence is important, especially when we're talking about chemistry, because it's going to allow us to determine which elements will join together with other elements. Let's move on to talking a little bit more about physics. And so energy is the ability to do work, and work is equal to force times distance. And there's a lot of different types of energy. We've got mechanical, electrical, thermal, radiant, chemical, nuclear, and what we're most interested in is electromagnetic, because remember, X-rays are part of the electromagnetic spectrum. So the electromagnetic spectrum, or the EM, spans a wide continuum of ranges of magnitudes of energy. So we go, for example, if you look at the drawing there, you can see you've got very, very large and long wavelengths like radio waves, all the way down to the very, very tiniest wavelengths, which are gamma rays. All waves of energy encompassed in the electromagnetic spectrum travel at the speed of light. So whether you're talking about a radio wave, a microwave, infrared, ultraviolet, X-ray, gamma, they all travel at the same speed, and that is the speed of light. So what makes one different from the other? Well, that is the wavelength and the frequency. So let's talk a little bit about that. Electromagnetic energy travels through space in the form of waves. And the distance between any two successive points on a wave is termed its wavelength. And this is represented by the Greek letter lambda. Wavelengths vary from kilometers to very, very small units called angstroms. So an angstrom is 1 times 10 to the minus 10th meters. Radio waves, very, very, very long wavelengths. It could be in meters or kilometers even. Important to note that X-rays have wavelengths between 0.1 to 0.5 angstroms. When we talk about wavelengths, we also talk about frequency. Frequency is the number of waves, how many waves pass a particular point in a given time. It too is represented by a Greek letter, and this is the Greek letter nu. Very important fact that we're going to use over and over again when we talk about X-rays and the physics behind them is that frequency and wavelength are inversely proportional. Frequency and wavelength are inversely proportional. So as one goes up, the other goes down. Let's talk a little bit about wave-particle duality. Wave-particle duality is the possession by physical entities such as light, X-rays, and electrons of both wave-like and particle-like characteristics. And on the basis of experimental evidence, the German physicist Albert Einstein first showed in 1905 that light, which had been considered a form of electromagnetic waves, must be thought of as particle-like, or localized packets of discrete energy, which we call photons. So even though an X-ray is not a particle, okay, it doesn't have any matter, can't weigh it, it sometimes acts as though it is a particle. There's a famous experiment that's down at the bottom there called the wave-particle duality experiment. So photon energy and frequency are directly proportional. What does this mean? If I increase the frequency, I increase the energy. So for example, in radiography, if I go from 70 kVp to 100 kVp, okay, I've got more photons that have a greater frequency from 70 to 100, and at 100 then, the energy is greater, it's more penetrating. So in the example to the right, A has a higher frequency than B. Therefore, the energy of A is greater than that of B. If we look at the diagram below, you can see some important terminology with waves. Generally, wavelength is crest to crest, but it doesn't have to be. It's from one part of one cycle of a wave to the corresponding part on the next cycle of a wave. You've got the amplitude, which is the height of the wave. You've got peaks, and then you've got troughs. And very importantly, when you look at the end on the right, one complete cycle. What is a cycle? A cycle is two alterations in a wave. So if you look at this wave, I've got a peak and I've got a trough. The peak would be one alteration, the trough would be another, one cycle. A little bit in review for the discovery of the X-ray. Remember, X-rays were discovered on November 8th of 1895. Rankine discovered them accidentally. He wasn't looking to discover X-rays, but he discovered them accidentally while working with what's called a Crookes tube. And this was at the University of Würzburg in Germany. And in 1901, Rankine did receive the first Nobel Prize in physics. So the first Nobel Prize was given to Rankine in 1901. Some interesting pictures here. We've got Rankine up at the top left, and of course there is the famous radiograph of Rankine's wife and the ring on her hand, the first radiograph. Down at the bottom, interesting, here is a picture of beginnings of fluoroscopy. So here you had an X-ray tube, not covered at all, man standing in front of it, doctor behind, looking into this viewing apparatus. The X-rays would go through the patient. They would strike a screen on the front of that viewing device, and then the doctor then would be looking at the screen. As you can tell, no radiation protection anywhere there. 1920s, up at the top, we started to incorporate a little bit more radiation protection. Fluoroscopy, 1940s, you still had the screen. Okay, the screen was being placed in front of the patient. X-rays are going through the patient. And then, unfortunately, the radiologist was getting a whole lot of radiation as well there. And of course, today we've got our modern CT scanners, which don't look anything like that older apparatus. Very, very important for you to know and to understand the properties of X-rays. Now, who came up with these? Rankine came up with these. The story is that when he discovered X-rays, he locked himself in his lab, and he came up with what we know as the properties of X-rays. And really, there's nothing that's been added to this list, which is pretty amazing. So what did Rankine come up with? He said that X-rays are highly penetrating invisible rays, which are a form of electromagnetic radiation. They are electrically neutral, which means they're not positive, they're not negative. They are polyenergetic and heterogeneous. Remember, when I set up 100 kVp on my control panel, very few of the photons are at 100 keV. We've got all these photons then that are at much less energy than that. So a beam of X-rays is polyenergetic, heterogeneous, many different types of energy. X-rays do release small amounts of heat when passing through matter. This is very minute amounts of heat. It's nothing that your patient is going to feel when they are irradiated. X-rays always travel in straight lines. They always travel at the speed of light. They can ionize matter. They can fluoresce certain crystals, which means when the X-rays strike certain crystals, it can cause them to glow. X-rays cannot be focused by a lens. X-rays do affect photographic film. X-rays do produce chemical and biologic changes in matter. That's why we need to be careful with radiation X-rays because they are ionizing, which means they have the ability to knock electrons out of the orbits of atoms, which can cause a whole bunch of different biologic changes in matter. And X-rays do produce what's called secondary and scatter radiation, which means that the X-rays enter into matter and they have the ability then to interact and then travel off in a different direction with less energy. And it's this scatter, for example, that we protect ourselves from in fluoroscopy. So when we're doing fluoro, the patient's being irradiated, we've got our lead apron on, we're protecting ourselves from scatter that's actually coming out of the patient.